Continuing our lesson on inverses, we see one more notable point, which is that the graph of the inverse is the reflection of the graph of the original function in the line y equals x. So in case you're not exactly sure what that means, let me show you. This is the question we did earlier. We had the 6 black points, and we took the inverse and we came up with 6 red points. Well, the line y equals x is a diagonal line which joins the points 1, 1, 2, 2, 3, 3, 4, 4, etc. So this diagonal line is the line y equals x. Well, if we were to reflect this point, draw a perpendicular line from this point to the line y equals x, and then continue on the same distance, again perpendicularly to that line, we would get to this point. Similarly, thinking of this as a mirror, the reflection of this point would exactly be this point. The reflection of this point would exactly be this point. Okay. The reflection of the point 0, 3 would exactly be the point 3, 0. Okay, we're drawing a perpendicular line through the line y equals x from one point to the other, and they're an equal space apart. In other words, this is acting as a mirror, and the red points are a reflection of the black points in that line. Now, it also works the other way. So we could look at the point we could look at the point 1, 0, and when we draw perpendicularly through the line y equals x, we see that the image of this point reflected in this mirror would be this point. And finally, we see that the image of this point perpendicularly reflected in that mirror line of y equals x would be that point. Okay? It actually works that way. And if you really wanted to see something cool, you could fold it right over that line. And if we were somehow able to make every black point leave a red mark when we folded it over, the black points would leave the red marks that you see. So it's a reflection. Similarly, we see that in this case, the red line drawn is a reflection of the black line drawn in the line y equals x. So we'll draw that graph here. The line y equals x looks something like this. My graphing leaves a little bit to be desired. I kind of missed it there. But if we were to reflect this black line in this mirror, we would get this red line. So the reflection of this black line would be this red line. If you want to see that on a point-by-point basis, imagine this point right there reflected through this line would get you to this point right here. Similarly, the reflection of this black line in the line y equals x would be this red line. Okay? So this black line reflected perpendicularly would get you to that red line, and vice versa. So the original function, the black one, reflected in the line y equals x gives you the red function. And if you, again, want to do the trick where you fold along the line, just imagine that if the black line could somehow, when folded over, leave a red mark, this black line would leave this red mark, and this black line would leave that red mark. Okay? It's a reflection of the line y equals x. Now, what we're going to do in this next situation is determine the inverse of each of the following, and then we're going to graph the original function and the inverse, and then state the slope and y-intercept of the inverse function. So the first one we have is y equals 4x minus 6. We're going to switch x and y so that we get x equals 4y minus 6. Try to isolate the y, add 6 to both sides, divide through by 4. We get y equals x plus 6 over 4. Now, since we have y equals x plus 6 over 4, we can determine the coefficient of x and the constant term, which is the y-intercept, and we get y equals 1/4 x plus 3 halves, so that's our inverse. And we can see that the slope of the inverse is 1/4, and the y-intercept of the inverse is 3 halves. And so, given that this is our original function, the black one, if we wanted to graph the inverse, we could recognize that the original function is a linear, so we're going to have a linear reflection. The reflection of a line is itself a line. The point 0, -6 will correspond to the point -6, 0, which is right here. The point 3 halves, comma 0 will correspond to the point 0, comma 3 halves. So this point corresponds to that point, and this point corresponds to that point. And we draw a straight line. And now we've just graphed the inverse of the function we were given. Okay. The next one is y equals -2x plus 3. Well, we're going to switch x and y and get x equals -2y plus 3. Subtracting 3 from both sides and then dividing through by -2 gives us this line right here. But we don't want to leave it like this because we might get mistaken and think the slope is 1 and the y-intercept is -3, when in reality we see the slope is -1/2 and the y-intercept is positive 3 halves. So we have a slope of 1 over -2 and a y-intercept of -3 over -2, or in other words, positive 3 halves. So the slope is -1/2 and the y-intercept is 3 halves. Given the original function here, y equals -2x plus 3, we see that it goes through the point 0, comma 3. So our inverse that we're graphing will go through the point 3, comma 0. Because remember, we're just switching x's and y's. So if 0, comma 3 is on the original, then it will map onto 3, comma 0 on the inverse because we're just switching x's and y's. Another point here is the point 3 halves, comma 0. So for us that becomes 0, comma 3 halves. And the inverse of a line is a line, and so that's our inverse function. Okay. We see we have y equals 2/3 x plus 1. Well, what we're going to do here is switch x and y. That'll give us x equals 2/3 y plus 1. Subtracting 1 from both sides gives us x minus 1 equals 2/3 y. We can isolate the y by multiplying both sides by 3 halves, and that gives us this equation here. And it's good to distribute that 3 halves in so that we know exactly what our slope is and exactly what our y-intercept is. The slope is 3 halves and the y-intercept is -3 halves. Now, the original function was y equals 2/3 x plus 1, and that's right here, y equals 2/3 x plus 1. Well, we see that that function goes through a couple of different points. One of those points is 1, comma 0, so our inverse will go through, one of the points is 0, comma 1, so our inverse will go through 1, comma 0. Another one of the points is 3, comma 3. 3, comma 3. Well, if you switch x and y from the point 3, comma 3, you see that the point maps onto itself, 3, comma 3. So the image of this point is itself. That happens every time the x and y coordinates are equal. And we can graph our inverse now by simply connecting up these points. Okay. And last but not least, we've got y equals 3 minus 1/3 x. What we're going to do is switch x and y. So we'll have x equals 3 minus 1/3 y. And we're going to do our best here to isolate for y. So subtracting 3 from both sides, and then multiplying both sides by -3 gives us this equation right here. And when we distribute in that -3 to determine the slope and y-intercept, we see that we get y equals -3x plus 9. The slope is -3, and the y-intercept is 9. Well, the graph of that looks like this. Okay, so we're going to graph the inverse. This point right here is the point 0, 3. So we're going to go to the point 3, 0, which is right there. This x-intercept is the point 9, 0. So we're going to go to the point 0, 9, which is right here. So the image of this point is this point, and the image of this point is this point, and we're going to draw a straight line between those two, and we've now determined the inverse of the original linear function and graphed it.